Hey, welcome back. Let's try another problem. 743 network delay times. Let's go ahead and read the question. So you are given a network of n nodes and labeled from 1 all the way to n, and you are also given the times, a list of the travel times as directed graph, and times I, and it's directed graph. So we are going from U to V, and the cost will be W, where the U is the source node and V is the target node, and W is the time it takes from single node to travel from the source to target. And we will send a signal from the given node K and return the time it takes from all the nodes to receive the signal. And it will be impossible for all the nodes to receive the signal and return -1. So if that's the case, we return -1. Otherwise, we return the time that we're going to pass the signal from one node, which is K, to all the other nodes. So basically, the question is asking that, hey, from one, for example, we have the source node is K. So we are starting from K, we are passing the signal. So at this, simultaneously, we're going to pass the signal to all the neighbors, right? We're going to pass the signal from 2 to 1. We're going to pass the signal from 2 to 3. And that's going to cost 1. Perfect. So this is going to cost 1. And my goal is to pass the signal to all the other neighbor nodes, right? So we're going to pass to 3, and 3 is going to pass to 4, and which is going to cost 4. And by the time we cover all the other nodes, that the furthest one is 4, and this is going to cost twice. The total cost is going to be 2. So we don't care about this guy because it's the direct neighbor. So by the time we pass to here, and we already passed to here, so they both cost 1. So this is not the furthest node we care about. We only care about the maximum time. So we are caring about what the least time we need to pass the signal to all the other nodes. So the question can also be translated to using Dijkstra, because in this problem, what the problem is asking is, you want to start from your source node, you want to pass the signal to all other nodes. So what is the shortest time we can pass all the signals to all the neighbors? But we want to find the shortest time. And that's actually translated to Dijkstra. So by using Dijkstra, and I think we did a couple problems before, and we want to track the minimum distance. So we're going to use a hash map store for each key, for each node, and we travel from the source node to that node. What is the shortest distance? We're going to store that in the hash map. And we're going to use another data structure, Q, to tracking the shortest distance, because Q has a property and is automatically sorted the values. Okay, sounds great. So let's go ahead and write the code. And we have a graph. So let's build a graph first, since we know that it's a directed graph. So we're just gonna build it as default dig. Oops, sorry. And then we're gonna put a dictionary inside of dictionary. And so for U and V and W, and that stands for our source and target and our cost. So our source to our target will cost W. So that's the weight we have. Perfect. So, and we need a heap. The heap is gonna be a list we build on top of list, and then we're gonna push our first pair in it. So we're going to track the distance. That's going to be our primary key. And we're going to sort it by the distance. So that's why we have 0 right there. And our initial position, that's our node. And we're going to put K. So K is going to be the initial position. Oh, by the way, this is lowercase k, right? That's lowercase k. Okay. And we put it there. And we put distance. And the distance is going to be a hash map. So we're going to put a hash map as well. And the value is going to be integer because we are tracking the minimum distance. All right, what else we need? So we can start exploring by using BFS. So we put Q right there, and then we pop out the time and stop. Time and node, actually. Time and node. And this is the distance, right? Distance stands for time. And we also have the node where we traverse up to. And we heap, Q, heap, pop. We pop this guy out from the queue, from the heap actually. So if the node is not being visited. So if we never store this value, and then we can start doing the calculation. So how do we do that? So we're gonna loop through the neighbors in the graph node because we built a graph already. So all we do is exploring from our source node. We're gonna explore all the neighbors and we're gonna track the distance, right? So we're gonna put the distance into our heap. So what we're gonna do is heap push, and we're gonna put all the distance in. So distance for current node, and we're gonna add the node. We're gonna add the distance we have in the current round. So the distance node stands for where we initially have, right? But when we go up to our neighbors, and we're gonna add up this particular edge value, and the edge value, fortunately, we already stored that into our graph. So all we do is adding up this guy into here, and now the node is no longer the node, it's the neighbor. So we're just gonna put that in neighbor there. Okay, so there's one more thing we need. Is we store the distance node will be equal to time, because we never tracked that before. So we have to track that right here. Okay, sounds great. And then we're gonna return. So what are we gonna return actually? So once we traverse everything, and we are gonna store everything, every single node, and also traverse up to this node, and what's the accumulated distance. So we're gonna store that into the value. So all we do is return the distance values, and we take the maximum value because we need the longest time. We need to find the path has the longest consume the longest time, and that's where we send the signal to every single node. All right. So, and one more thing, sometimes, for example, we have a isolated node. We are not even sending the signal all the way to here. So in that case, we need to do a separate check. So if the length of the distance is not equal to n, that means we are not even able to reach there. So we just return -1. Otherwise, we return this. Heap. Okay. Okay, looks good. So the way we do that is, let's think about it. We build a undirected graph, and we have our heap to storing our distance, and we also store where the node up to. So initially we just put the initial node, which is the source node right here. And we also need a distance hash map to storing all the distance we have, the shortest distance. And we're gonna use the heap to sort our distance. And each time we just deal with the node has the shortest distance. We pop this guy out. We check, hey, if this guy is already being calculated. If not, let's do some calculation. So let's store the current node equal to the time. And then we explore all the neighbors. And then we add up the current layer. And then we keep going.